All right, I think we're good. Okay, so 2-1, linear and quadratic functions, where we're going to start in Chapter 2. So Chapter 2, like I said, is all about polynomial functions, but we're going to focus on the linear and quadratic varieties today. If you look in your textbook, don't take it out right now, but if you were to look in your textbook, they do have a definition of a polynomial function that I think might, upon first glance, look a little bit confusing. I'm not going to have you write it in your notes, but I just want to show it to you just so I can kind of explain a little bit about what exactly they're talking about here. So they give you this definition. It says, let n be a non-negative integer and let all these a's, a0, a1, a2, etc., 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 all the way up to an, be real numbers with an not equal to 0. The function given by all of that is a polynomial function of degree n with leading coefficient a sub n. Okay, so what in the world are they talking about there? Well, I'm kind of trying to decipher this a little bit for you here. Do you see how this has a bunch of terms that are all added together here? Okay, they're kind of ugly looking right now, but it's essentially a bunch of terms that are all just getting added together. Okay, and each one of those terms has an a times x to a power, right? And each one of these little a's in front has a subscript. This is a sub n minus 1, and this is little dot, dot, dot here in the middle is etc., 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 until we get all the way down to a sub 2, a sub 1, a sub 0. They use n because we don't know where we start. We don't know how many terms this thing has, because a polynomial could have any number of terms added together. So n, we're assuming, is the first one, and then we're going to count down from n all the way to 0. Okay? But basically, all you need to know is that all these little a's with the subscripts are coefficients. And what's a coefficient? Yeah, it's the number in front of x that you're multiplying by in an equation. Okay? So we have all these little coefficients a. That's what all of these are that it's talking about. Okay? Don't worry about the subscripts. It's just a notation thing to count how many of them there are. So we have a bunch of coefficients, all multiplied by x, raised to some power. Okay? And the powers start at n and also go down, etc., 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 to 1, 0. Okay? So a polynomial function is a summation of a whole bunch of terms where you have a coefficient times x raised to a power, and each one of those terms, that power is decreasing, 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 all the way down to 0. Does that make sense? That's what a polynomial is, kind of in layman's terms. I think it's an easier way to think about it. Something times x to a power, the powers go down. That's a polynomial. Okay? It does make note here at the end, the 0 function, f of x equals 0, is a polynomial function. It has no degree and no leading coefficient. So if the power is 0, the leading coefficient, or the coefficient is 0, it's still technically a polynomial function because it still fits the definition. Okay? It's just that all these little a's then would be equal to what? What would every coefficient be? 0, right? So if every single coefficient is 0, then you have what's called the 0 function, which is still a polynomial. It just has a degree. It has no degree and no coefficient at that point, but it still technically works. Now, the ones that we're going to take a look at, and these we will write down here in just a minute. Okay? We're going to talk about these guys. Okay? The 0 function we just did. There's the constant function, f of x equals just some number, a. A linear function, ax plus b. You guys are probably better suited to mx plus b. You've seen it that way, right? Okay, m is just a variable, though, right? It doesn't have to be the letter m. It could be anything. So we use a and b because they're alphabetical. So ax plus b instead. And then there's the quadratic function, which you guys should be pretty well acquainted with at this point, ax squared plus bx plus c, right? In all of these last three, a is not equal to 0. And the reason that a is not equal to 0 is because if you didn't have that first term there, if this was 0, what would the constant function be? It'd be the 0 function, right? And if a were 0 in the linear function, what would the linear function be? The constant function, right? And same thing with quadratic. If there was no leading term on the quadratic function, there's no x squared in there anymore, then it's a linear function again, right? So the leading coefficient has to exist for us to be able to define them this way. And then there's the degree listed over here as well, which is basically the highest power that you see in the form. Okay. So in our notes, though, let's quickly jot these guys down so that we have them. So the zero function, f of x equals 0, and we'll just quickly list the degrees here as well. Constant, f of x equals a, and, oh, I'm sorry, the degree is not 0 on this one. It's kind of an NA situation. Doesn't have a degree. This one, the degree is 0. Linear, which you guys spent like half of Algebra 1 talking about, is ax plus b. That has a degree of 1. And then the quadratic, f of x equals ax squared plus bx plus c. And that's got a degree of 2. Okay. So, and today, like I said, we're going to focus on those two. Okay, linear and quadratic. So, in looking at linear functions, what sorts of graphs do linear functions have? It's not a trick question. Lines, right? We've done tons of these in the past, right? Anything that graphs a line. All right, and there are some important attributes to a line that we will study, and you have studied. And those two things, or the two that you normally are looking for, are the slope of the line and some sort of intercept. Usually the y-intercept is the one that you're given or you're trying to find because that's the easiest to make an equation out of it. Okay, so here's what we're going to do. We're going to analyze a linear function, and I'm going to give you a couple of points that it goes through, and we're going to see if we can then piece together what the slope of the line would have to be, and then because of that, then what the equation of the line is going to be. There you go. Okay, so we're going to say assume f of x is linear and f of negative 1 equals 3 and f of 2 equals 9. And so we're going to develop an equation for f of x. Okay, now this is written in a way that you probably haven't seen before with this type of thing. This f of negative 1 equals 3, f of 2 equals 9. In the past, when you were doing this kind of thing, you were probably just given 2 points. Well, I really did just give you 2 points. I just wrote them in function notation. So if f of negative 1 equals 3, what ordered pair is that? What point is that? It's negative 1, 3. Yeah, okay. So we have the point negative 1, 3, and then 2, 9, right? So the first thing we're going to want to do is to take those 2 points and calculate a slope. Okay, or rate of change is another name for slope. Okay. So I'm going to call it rate of change, just so we're using the new vocabulary here. Okay, so if we get those 2 points, how do we calculate the rate of change, or slope, like we've done in the past? Yeah. You're close. Other way around, right. Difference in the y's divided by the difference in the x. So delta y divided by delta x. If you guys have seen the little triangles before, maybe in physics or something, I don't know. But that basically just means change in y divided by change in x. Okay. So a couple different ways you can think about this. You can go through and subtract the two numbers. 9 minus 3 would be the difference in the y. 2 minus negative 1 would be the difference in the x. I tend to just look at the 2 points and think about counting from one to the other. So, like my change in my y, if I start at 3 and I end up at 9, what's the change? 6. My change in x, if I start at negative 1 and I count up to 2, what's the change? 3. Okay? So, I think it's easier to do it that way, but you can just subtract the two numbers and you got it. So, but in any event, the change in y is 6. The change in the x is 3. So what's our slope? 2. Okay. So we know our slope is 2. So using that, we can start to kind of piece this equation together now. So it's going to be a y equals 2x plus, and I don't know the b yet. So what could I do to find the value of b, given the information that I still have available to me? Yeah? You got it. Take one of those 2 points, plug them in for x and y, solve the equation for b, then you got it. So whichever one is your favorite, doesn't matter. I'm going to take the second one because I don't like negatives. So 9 equals 2 times 2 plus b. So it would appear as though b would need to be 5 to make that work. So my final equation, and I'm going to make it f of x because it's asking for f of x. It's going to be 2x plus 5 would be that equation. Okay, so that's just using our information to help us come up with an equation for a line. And that's about it as far as what they're going to have you doing with lines. As far as the equation side of things, the only thing you're going to have to really do with lines is if we're looking at like a correlation type thing. 922. There you go. Okay, so just real briefly, let's talk correlation. You're not actually going to be doing any lines of best fit or that sort of thing on the calculator, but they do kind of offhandedly mention a little bit of correlation stuff here. So just wanted to go through this. It's kind of random, I know, but so if you've got some kind of scatter plot, okay, and it seems like the dots are all clustered together, so it appears to be pretty linear, okay, we would call that a strong correlation. And if it appears as though the slope of the line is positive, or it's increasing, then we would say it's a strong positive correlation. So this example that I have right here, this is a strong positive. So likewise, a strong negative would be, it's still all clustering around what appears to be a line, but it's decreasing. So strong negative. And then we've got weak positive and weak negative, and you can probably guess what those look like. If it's a weak correlation, then it's not real well clustered together, but you can kind of still tell, maybe something like that. You can tell, okay, it's going up, positive-ish, but they're not real tight together, so that would be a weak positive. And then a weak negative, you can probably guess. Not real tight together, but appears to be heading down. So something maybe sort of like that then, okay? And then if the dots are completely random, if there's no way to identify if it's increasing, decreasing, or whatever, for those we just say no correlation at all. Okay, so you really have 5 different options. Is it strong or weak? Is it positive or negative? Or is it simply just no correlation at all? Doesn't appear to be anything linear whatsoever. Okay, so I wanted to get into quadratics because that's going to be the main focus of what we're doing in section 2.1, but we did have this little bit of linear stuff we needed to kind of get through here. So, quadratic functions. They come in 2 varieties. There are quadratic functions that are written in standard form and quadratic functions that are written in vertex form. Okay? So standard form we've already seen. And this is the one you're probably going to use the most. Okay, that one. That one you're going to probably use the most because it lends itself to the quadratic formula, okay, with the A, the B, and the C and all of that. It's written in a form that's a lot like the other ones too. So we tend to want to use standard form. Now, the vertex form, if our goal is to try and graph the thing, vertex form can be a little bit more helpful. And that one looks like this. Okay, where the H and the K are the vertex, the coordinates of the vertex. So what is a vertex of a quadratic? Think about the graph of a parabola. Yeah. Exactly. It's that highest or lowest point on a parabola. Okay. So if we know the coordinates of a vertex, that's useful information if our goal is to try and graph the equation that we have. Okay. So we're going to look at that. So if we have like an equation in standard form, and let's say we want to draw a graph of it, we're going to want to take that standard form equation, convert it into vertex form, and then use that vertex form to help us put a graph together. Okay? And so there's some different information that we can use to help us do it. Okay? So let's say that we've got, for example, a quadratic that's in standard form. How about 3x squared plus 12x plus 11. So we're going to take this guy, going to convert it into vertex form, and then use the vertex form to identify where the vertex is, and then graph the thing. Okay? All right, so putting it into vertex form is going to include the process of completing the square, which you guys did in Algebra 2 as well, to solve quadratics. Okay, it's not the same exact process of completing the square that you did in that case, because like I said, it was a different goal. The goal you had there was to solve a quadratic, to find the zeros and that sort of thing. And that's not what we're doing here. So this process actually ends up a little bit easier. But what we're going to do is, remember, we're trying to get it to look like this. So the first step that we do is we factor a number out of the first 2 terms only. So we can take a 3 out. So it looks like that. Okay. Now, do you see how we're getting there? Okay? We know A, and we know K. Now, the trick here is going to be in figuring out H, because what we have in the middle is not exactly the way we want it to be yet. Notice how it needs to be an x minus h squared. And right now, we've got x squared plus 4x. Okay? There's nothing squared on there yet. So what we need to do is we need to take whatever's in that little parenthesis there, and we got to complete that square. Okay? So what makes this thing, we have to add something to it. What makes that thing a perfect square? Anybody remember that process? How we figure out what that number is we need to add on the end to make it a perfect square? You're close. It's half of this squared. Okay? So take that second number, 4, chop it in half and square it. So 2 squared, 4. Okay. Now, hold on a second. Haven't I just changed my function, though? Not just the look of it, but literally changed the value of it, too? I just added a random 4 in the middle? You're not supposed to be able to do that, right? In algebra, I can manipulate things, but I have to do the same thing to both sides of an equation. I have to make sure things stay balanced and all of that. I can't just say, oh, I need to put a 4 in the middle. I'm going to put in a 4. What? You can't do that. So, to keep this thing in balance, I need to, at the end of it, also add something to offset what I put in there. Negative 12. Good. Okay, so catch why that is? It's not just the 4, right? There's this 3 out front. It's technically what I added to the entire equation by putting this little plus 4 in the parentheses. Is I actually added a 12 because it's 3 times 4 if I were to distribute that 3 back through there. So to offset this thing that I did here, I have to subtract a 12 or add a negative 12, however you want to look at it. So, yeah, that's got to go there. Okay, and so now I can simplify up a little bit. First of all, x squared plus 4x plus 4, what is that written as a perfect square? X plus 2 squared, right? So 3x plus 2 squared. And then I've got this plus 11 minus 12. So what's that? Minus 1. And voila, I have it in vertex form. So what's my vertex? So it's minus h and plus k. So what's the h? Negative 2. And what's the k? Negative 1. Mm-hmm. Yep, so the vertex of that parabola is at negative 2, negative 1. So, if I'm going to start piecing together a graph here, I know that my vertex needs to be at negative 2, negative 1. Okay, so hooray, I got 1 point. That doesn't really tell me the whole story, though. So what else do I know about this parabola given its original equation? Yeah? Yeah. Because in vertex form, it is always x minus the h. Right now I have x plus 2, so technically that h would be a negative 2. You've got to switch the sign on it. Okay, so some other information about parabolas that you guys have studied in the past. How do we know if the parabola opens up or down? What tells us that? Yeah. Mm-hmm. What about that leading coefficient? Right. Okay, so should this parabola open up or down then? Up, because our original leading coefficient was a positive 3, right? So you know it opens up. Okay, so I'm going to give it a little opening up there. I don't know quite how wide yet, but I know it's going to open up. And then one other piece of information that you can use to help you kind of see how wide or skinny this thing is the last number here in the original equation, that plus 11. What is that plus 11? It's a y-intercept. Just like the number added at the end of a line is the y-intercept. Same thing with any polynomial, including a quadratic. Just think about this. If you were to plug in 0 for x, right? That's doing a y-intercept. If x is 0, what's the y? Well, if I plug in a 0, these first two terms go away and I get 11. So up this y-axis, I should have an intercept at 11. Okay, now the way I drew my scale, that's going to be up there a ways, because right now the way I was just counting by ones. So basically what that tells me, though, is I know that, yeah, this is where my vertex is, it opens up, but this thing is going to be a pretty darn skinny parabola. So it probably looks something about like this. Okay, so we got a good sense of what the graph of that thing looks like. So if I give you an equation in standard form of a quadratic, one expectation is going to be that you can sketch a graph of it effectively, using a y-intercept and knowing which direction it opens up or down. Okay, so let's jot down some of that information we just talked about that helped us do that. Okay, so the opening up and down, so if A is greater than 0, or if it's positive, that means it opens up. If that leading coefficient A is less than 0, it opens down. And then we also use C to help us out. That's a y-intercept, which will help give you an idea of scale as far as how much it stretches out, that sort of thing. Okay, now something else to think about, kind of relate back to some things we talked about in Chapter 1. If you look at this equation in vertex form, there should be something a little familiar about the way this thing is written. Remember in Chapter 1 in Section 1.6, we were talking about transformations, stretches and shrinks and slides and all that kind of stuff, translations. Do you guys see a translation in this equation? Horizontal and vertical? Okay. What's the horizontal translation in there? Yeah. Left 2. And what's the vertical translation in that equation right there? Down 1. Do you see that in the graph? See how we've just taken x squared, we've moved it left 2 and down 1? Okay. Vertex form, really, all it is showing you the translation. Okay. So it does give you the coordinates of the vertex, but ultimately it's what we've already talked about with any function. It's showing you how far it's moved left or right and up and down to place that new vertex, which originally was at 0, 0, in a new location. Okay. So I think it's helpful to think of it that way too, so that you can see where that thing's going to land. Let's see. Oh, all right. That being said, there is a shortcut to get to the vertex if you have something in standard form. Okay? So I would be remiss if I didn't show you that, because it is helpful for a lot of people to do it this way instead. And this is a formula that, again, should look familiar. So the shortcut to the vertex, if you have something in standard form, f of x equals ax squared plus bx plus c, the x-coordinate of the vertex, negative b over 2a. Does that look familiar to you? You've used it before. Maybe you don't remember, but you have. And then if you want the y-coordinate, it is f of that. You plug that number into the function, and that'll give you the y-coordinate. Okay? So let's take our last example, and we'll quickly get the vertex. The answer should come out to negative 2, negative 1, right? So if we've got this f of x equals 3x squared plus 12x plus 11. Whoops. So let's say my only goal is to find the vertex. I sit there and do all that completing the square. I don't need to graph the thing. I just want the coordinates of the vertex real quick, and that's it. So the x-coordinate of that vertex, negative b, negative 12, divided by 2a, 2 times 3. Okay, so what is negative 12 divided by 2 times 3? Negative 2. Okay, and then if I want the y-coordinate of the vertex, I do f of negative 2. So 3 times negative 2 squared plus 12 times negative 2 plus 11. So just plug it in. And this is going to be 3 times 4, that's 12, minus 24, plus 11. So that would be negative 12 plus 11, negative 1. And look at that. X is negative 2, y is negative 1. So our vertex is the point negative 2, negative 1, just like we found before. Okay? So, like I said, if the only goal of the problem is to find the vertex, then there you go. Okay? Now, that being said, you can use this trick to help you even if the problem asks you to write the equation in vertex form. You don't have to complete the square necessarily. Because once you know the vertex, think about it. This thing into this form. My pencil stops breaking. If the goal was to put it into vertex form, so that would be a times x minus h squared plus k, right? If you remember what this form looks like, that it's set up like that, you already have the h and the k now, right? The h is negative 2 and the k is negative 1. So without having to complete the square, okay, assuming I didn't do any of that work, just doing the little shortcut here, I could do, okay, I got x minus negative 2, so plus 2 squared, and my k is negative 1. I've got that much. What's the only thing I have left that I need to find? A. Well, if I started with the equation in standard form, guess what? You have A. Here's my original equation, right, once it focuses. Right here. What's A? 3. Oh, sweet. Okay. Done. So there's really no need to complete the square. However, I felt like it's important to show that to you because it does get used for other things later, but there's a way around it if you want. Okay. So, talking about that, we need to move into finding zeros, which is a lot of what we're going to do down the road. Okay, and a lot of what you did in Algebra 2. Okay, so this should be very familiar. Okay, and you guys had, remember this in Algebra 2, there was a whole chapter on finding zeros of quadratics, and each section was a different method that you used to get the zeros. Does anybody remember a method that we used in Algebra 2 to find the zeros of a quadratic? Quadratic formula. Quadratic formula is the pro of the quadratic formula always works. You can always rely on the quadratic formula to get you what you want. Drawback of the quadratic formula, it's messy. Yeah, it takes some time, and it's easy to make mistakes in the middle if you're doing it by hand, that sort of thing. But pretty good, pretty decent go-to. Any other methods you guys remember that you used? Factoring. Yep. The pro of factoring, if the equation factors, it's generally pretty quick. The con to factoring, sometimes it's difficult to factor. Or maybe sometimes it doesn't factor at all, in which case that method doesn't work at all. Okay? But that's a good one. What we're generally going to do is check to see if it factors. If it does, do that. If it doesn't, go to the quadratic formula. Okay? So these are going to be our big two that we'll focus on. Now there are some other methods that you guys did, okay, which we are not going to generally look at, but still work. One was completing the square. Okay, it works, but the thing is it's messy and easy to make mistakes, that sort of thing. Quadratic formula, I think, is a little bit more straightforward and reliable. Graphing is the other thing, which we will touch on some when we start talking about some of the calculator stuff we're going to do with this. I mean, if you can graph a quadratic on your calculator and then look for the x-intercepts, okay, yep, that works. Okay, but assuming that we don't have a calculator to work with, we're really just going to rely on the top two. Okay, so like I said, our method is going to be number one, check factoring. So if it works, obviously use it. If not, then we're going to go to the quadratic formula. And we should probably, for those of us that don't remember it, write down this quadratic formula that we speak of here, because we're going to be using it quite a bit. So negative b plus or minus the square root of b squared minus 4ac all divided by 2a. If you don't have that memorized yet, you should. Okay, and I think by the time we get to our first quiz, we'll have used this thing so much that you probably will just have it memorized anyway. But if you don't, I mean, that's just something you need to know. That's a pretty standard equation that we're going to continue to use this year and in AP Calculus quite a bit. That just got to know it. So, all right, so let's see if we can use this guy to help us. Okay, so remember, first we're going to check for factoring, then see if it doesn't work, use the formula. So let's find the zeros of f of x equals x squared minus 19x plus 90. We'll start with that one. Okay, so our factoring, the way that we approach that depends on the equation. If it's one like this, where there's just a 1 for a, those are the ones we want, because then the process becomes pretty simple. You're just looking at these back two numbers then. And what do we want to know about these back two numbers? How do we use them to help factor it? Plug in those two numbers? Well, we're not using the quadratic formula yet. So how do we use it to factor, though? Yeah.
What adds into negative 19 multiplies to 90?
Right. We're looking for two numbers to help us factor. And those two numbers have to add to negative 19 and multiply to 90. Okay? So, we know what those are? Negative 9 and negative 10. Mm-hmm. So this is going to be f of x equals x minus 9 times x minus 10. Okay, so that's the factored form of this quadratic. So then what are the zeros? What numbers, when I plug them into that, make the equation come out to 0? 9 and 10. Positive 9 and positive 10. Okay? So it's always the opposite of whatever the sign is on these guys. Positive 9, positive 10. Alrighty, let's try another one. So let's do f of x equals 3x squared. Let's see. Minus x minus 4. So again, first thing we're going to check to see is, can we actually factor this thing? Oh, whoops, hold on a second. I think I did that backwards. This should be plus 11 in the middle, sorry. I was quickly multiplying it in my head and it didn't work. It would have worked too? Oh. Yeah, okay. Well, anyway. We're going to do this one instead. So, now if I have a coefficient on x squared, okay, I can't go back to the well like I did here and just look at these back two numbers to try and factor it, okay? Because I'm not accounting for the fact that this is now a 3 in the front instead of just a 1. Okay? So we had a process for these guys, too, to factor them. Anybody remember what we do to get started on these? Yeah. Okay, so the a and the c get multiplied together. In this case is negative 12. And so now we look for two numbers that multiply to this, negative 12, and add to 11. Okay, so can we come up with two numbers that make that happen? Can we multiply two numbers and get negative 12, but add two numbers and get 11? 12 and negative 1. Right. Now, that doesn't mean that that's the way I factor it, though. It's not just x minus 12 and x plus 1. Or what do we say? X plus 12 and x minus 1. That's not the factor. An easy trap to fall into. Okay? A lot of people would be like, oh, okay, so 12 and negative 1, so there, factored it. What's wrong with that? Yeah, try multiplying this back together. Do I end up with this? No, right? I don't have that 3 in the front anymore, exactly. And in fact, I'd have a minus 12 in the back, and there should be a minus 4. It just doesn't work, okay? So that's with those two numbers. What we're doing with those two numbers is we're using them to help break up the polynomial into 4 terms instead of just 3. So that we now get 3x squared plus 12x minus 1x minus 4, like that. And from here, we use the technique of grouping to factor it the rest of the way. We group the first two terms together, we group the last two terms together, factor out a GCF, factor out a GCF, and go from there. So just the first two terms, what's the greatest common factor? 3x. So if we take out 3x, we have x plus 4. What's the GCF of the back two? Negative 1, x plus 4. Okay, so then we're going to end up with our two factors are actually 3x minus 1 and x plus 4. So now I can look at my two factors and come up with my zeros again. Oops. One of them's probably pretty easy. The other one you might have a little trouble with. So give me the easy one. Negative 4. Okay. Again, as soon as we have a coefficient on these guys, people tend to struggle with it. 3x minus 1, what number, if I plug it into that, is going to make that 0? Yeah, 1/3. Okay. Kind of the trick to remember what that is. Yeah, it's this number, change the sign, positive 1, but then divide by this. 1 over 3, 1/3. Okay, and think about it. If you plug in a 1/3, 3 times a third is 1. 1 minus 1, 0. That's what we want. We want it to come out to 0. So 1/3 would be the other 0. Okay. So both of those we were able to factor. Just one was easy, one was a little more difficult. So if let's say the second one, I wanted to just go and use the quadratic formula instead. So, okay, so I'll just show you that process. So this is doing the factoring route. Over here, we'll quadratic formula the thing. So A equals 3, B equals 11, C equals negative 4. So then we've got x equals negative 11 plus or minus the square root of b squared, 11 squared, minus 4ac, all divided by 2a. So when working with the quadratic formula, to be safe, just under the square root first, get that down to one number, and then from there it's usually not too bad. So negative 11 plus or minus the square root of, looks like 121, 4 times 3 times 4 is, it'd be 12 times 4, so 48. So plus 48. And all of that divided by 6. So that's going to be plus or minus the square root of 121 plus 48 is 169. What's the square root of 169? 13. So negative 11 plus or minus 13 over 6. So if I do negative 11 plus 13, that gives me 2. 2 over 6, 1/3. And then if I do the subtraction, negative 11 minus 13 is negative 24 divided by 6, negative 4. So same two answers. Okay, so yeah, like I said, quadratic formula, it always works. So if you don't like to do the factoring, you can just jump right in and do that instead. Very last thing, and then I am done, I swear, is I forgot to do this. I should have done this when we were talking about vertex form. But there are going to be some questions in your homework, and I inevitably get people confused by them every year, so I just wanted to do one with you. We're going to find the equation of a parabola with a vertex given. So let's say equation of a parabola with a vertex at 1, 3, and it's also going to go through the point, bless you, let's say 4, 12. Okay, so if we were to look at just a quick sketch of this thing, so at 1, 3, there's the vertex, and then it's going to go through 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So then 12 is like up here somewhere. Here's 4. So we've got a parabola that looks kind of like this. Okay, yeah, I know. It's not to scale, but you get the idea. So it has that vertex though at 1, 3, and then it has to go through the point 4, 12 as well. Okay. So what we can do is, since we know the vertex, what form of a parabola do you think is going to be good to start with here then? Yeah, if we start in vertex form, and just plug in our h and our k, we're already most of the way there then. So we have a times x minus 1 squared plus 3. Okay? Now, we have this other point, 412, that we can still use. And what's the only other thing we need to know about this equation to write it out completely? A. So what do you suppose that can do? Yeah, if I use this point, right? This point is another x and y that is on that curve, right? So if I plug in that x and that y, I can then solve for a, and I got it. So that's what I'm going to do, because this is actually just y, right? F of x and y are the same thing. So I've got 12 equals a times 4 minus 1 squared plus 3. So 12 equals 4 minus 1 is 3. 3 squared is 9, so I got 9a plus 3. 12 minus 3 is 9, so 9 equals 9a, so a is just 1. Okay, did some quick algebra there. And so then my equation, then I can leave it in vertex form because it didn't tell me which form it wanted it in. A is just 1, so it's just going to be x minus 1 squared plus 3. Like that. Okay? So you can do problems like that too, using vertex form. Okay? It's just a little bit of different information they're giving you to start. Okay, I'm done, I swear.